Assalamualaikum everyone, welcome back to my YouTube channel. Today we are going to discuss the model textbook of physics for first year, and today the chapter we are discussing is chapter number 8, and we are going to complete the short conceptual question answers of this chapter and the remaining which were left. So let's get started. So the question we are going to continue from question number 16, which is what are the similarities and differences of the refrigerator and the air conditioner? So the similarities between them is both operate on a vapor compression refrigeration cycle. Both use a compressor, condenser, expansion valve, and an evaporator. Both absorb heat from the cooler region and reject it to the warmer region. Both use a refrigerant to facilitate heat absorption and rejection. Both require electricity to operate. And the differences between them is a refrigerator, a small enclosed space, fridge interior, and the air conditioner is large space like a room or a building. Refrigerator absorbs heat from inside the fridge, while the air conditioner absorbs heat from the indoor air. Refrigerator releases heat into the kitchen or surroundings, while air conditioner releases heat outside the building. Refrigerator preserves food and perishable items, while air conditioner provides comfort and cooling for people. Refrigerator minimal airflow mainly maintains low temperature, while the air conditioner actively circulates cool air using a fan. Refrigerator much lower, typically from 2 to 5 degrees centigrade for the fridge and -18 for the freezer, while the air conditioner is higher, that is 16 to 30 degrees from room cooling. Next question, we have question number 17, which is what is meant by reverse entropy and what is the significance of entropy explained. The answer to this is reverse entropy refers to the decrease in entropy, meaning a system becomes more ordered. It occurs in a non-isolated systems where external energy is used to reduce disorders. For example, living organisms use energy from food or sunlight to maintain order and reduce entropy locally. Significance of entropy is the second law of thermodynamics. Entropy always increases in an isolated system, determining the natural direction of the process. The irreversibility indicator, higher entropy means more disorder, making process irreversible. For example, heat always flows from hot to cold. Third point is energy quality measurement. More entropy means energy is less useful for doing work. For example, thermal energy in the surrounding is unusable. Fourth, we have role in thermodynamic cycle, help analyze efficiency in engines, refrigerators, and power plants. Next question, we have question number 18, which is what is the difference between heat transfer and the thermodynamics. So the heat transfer studies the mechanism of heat movement from one place to another, while thermodynamics studies the energy transformation between heat, work, and internal energy. Heat transfer concerned with how heat moves, that is conduction, convection, and radiation, while thermodynamic concerned with why and how energy changes occurs in the system. Heat transfer deals only with the heat energy transfer, while thermodynamics include heat, work, and energy conservation. Heat transfer uses principle of conduction, convection, and radiation, while the thermodynamics based on the law of thermodynamics for second and third law. The example of heat transfer is heat transfer from the hot coffee cup to the surrounding air, while the thermodynamics analyze the efficiency of an engine or refrigerator. Next question, we have question number 19, which states that the coffee filled in a thermos is vigorously shaken. So has any work been done to the coffee? The answer to this is yes, work is done to the coffee because shaking applies a force that causes motion, which transfers energy to the liquid. And the second part is that the internal energy of the coffee changes. Yes, the internal energy increases due to the mechanical work done by shaking, which increases the kinetic energy of coffee molecules. Number third is, does the temperature of the coffee rises? Answer to this is yes, and internal energy increases, molecular motion increases, leading to the slight rise in the temperature. Does the coffee get heat from outside? No, the thermos is insulated, preventing external heat transfer. The temperature increase is solely due to the work done on the coffee. Next question, we have question number 21, which is what are the conditions for the thermodynamics equilibrium? So the condition for the thermodynamic equilibrium are thermal equilibrium, which means that no temperature difference, no heat flow. Second is the mechanical equilibrium, which means that no balance forces, no pressure changes. Third is chemical equilibrium, no net chemical reactions or mass transfer. A system must satisfy all three of these conditions in order to be in the thermodynamic equilibrium. Moving on to the next question, that is question number 22, which states that when internal energy of the system rises, can its temperature stay same? So the answer to this is yes, internal energy can rise without temperature changes in cases like phase change. Energy is used to break molecular bonds, for example, melting or boiling. Next is potential energy increase. Energy is stored without increasing molecular motion. And the third is chemical or nuclear reactions. Energy is stored in bonds without immediate temperature rise. Thus, temperatures stay constant if energy increases as latent heat, potential or chemical energy instead of a kinetic energy. Moving on to the next question, we have question number 23, which states that when a car is driven at a certain distance, why does the gas pressure increases in the tire rises? When the car is driven, the gas pressure in the tire increases due to following reasons, which are frictional heating, the tire root contacts, and air compression inside the tire generate heat, raising the air temperature. Increase in temperature according to the Gay-Lussac law, which is pressure is directly proportional to temperature at constant volume. As temperature rises, pressure increases. Third is air molecule motion. High temperature increases the kinetic energy of the air molecules, causing more frequent and forceful collisions with the tire walls, increasing pressure. Next question, we have question number 22, which states that prove the area under the PV graph is equal to the work done. As we know that the work done by the gas is equals to the sum of pressure and volume. This means work is the sum of pressure multiplied by the small volume changes. Understanding the PV graph, the x-axis represents volume and the y-axis represents pressure. Work is calculating by adding up small steps of pressure and volume, which forms area under the curve. For the simple cases, constant pressure, the gas is rectangle, and work is W is equals to Vf minus Vi, which is just length into a height, which is further is equals to the area of rectangle. So the work done is still total shaded area under the curve. Question number 25. We have all the reactions going on the refrigerators or the thermal. We have to explain it. So for the constant temperature, the fridge maintains a nearly constant temperature inside. Heat absorption and release, the refrigerant absorbs and releases heat without changing temperature. Phase change, the refrigerant evaporates and condenses isothermally. Since temperatures stay nearly constant, the refrigeration process is isothermal. The last question we have, question number 26, which states that define reversible, irreversible, and cyclic processes. So the reversible process is a process that can be reversed without leaving any change in the system or surroundings. It happens infinitely slowly and and is in continuous equilibrium. Example for this is slow compression expansion of a glass in a frictionless piston. Second, moving on to the irreversible process, it is a process that cannot return to its original state without changing in the surroundings. It occurs naturally and quickly, often involving friction, turbulence, and heat dissipation. The example for the irreversible process is free expansion of gas in real life engine cycles. Third, we have cyclic process, which is a process in which a system returns to its initial state after a series of changes, and the net change in the internal energy is zero. And the example for the cyclic processes is Carnot cycle and the refrigeration cycle. So with this, we are done with the chapter number 8, conceptual questions, and completed. So if you like the video, like, share, and subscribe, and we'll see you in the next lecture.